Okay, let's dive into this. Have you ever just stopped and wondered why abstract equations, like things we literally just dream up in our heads, somehow act as the absolute source code for physical reality? It's kind of crazy when you think about it. It's the exact reason the atoms in your body hold together and why stars burn. Welcome to This Explainer. Today, we're unraveling what is basically a cosmic detective story about how abstract math perfectly and honestly almost inexplicably predicts the universe around us.
To really get at the heart of this mystery, imagine you invent a totally new, purely abstract kind of geometry, just for fun, no practical application whatsoever. Well, that's exactly what Bernhard Riemann did back in the 1850s. Then, over 60 years later, Albert Einstein is pulling his hair out trying to figure out how gravity warps space-time, and he discovers that Riemann's abstract, totally made-up geometry is exactly, perfectly, the language the universe actually uses. Nobody planned this perfect fit. So, we really have to ask, why on earth does the universe speak math?
This whole puzzle was beautifully articulated back in 1959 by the Nobel Prize-winning physicist Eugene Wigner. He basically viewed this deep connection as a miracle, and he broke the mystery down into three specific layers. First, you've got the descriptive layer, like why can nature be described by math at all, instead of just being a chaotic mess? Second, there's the precision layer. Why does it work so incredibly well, down to 15 decimal places? And third, the predictive layer. How does math invented for one abstract reason suddenly become the absolute perfect tool for a completely different physical reality centuries later?
Section 1. The evidence. Predictions before the fact. So let's interrogate this historical evidence, really looking at those moments where mathematical concepts got their way before the physical discoveries did.
You know, the conviction that nature has this deep underlying mathematical structure, it definitely didn't happen overnight. It built up over centuries. Going all the way back to 570 BCE, Pythagoras noticed that musical harmony corresponds perfectly to whole number ratios. Not roughly, but exactly. Then by 348 BCE, Plato is mapping elements to geometric shapes. Fast forward to 1642, and Galileo essentially declares that the universe is written in the language of mathematics, backing it up with his laws of falling bodies. And then, the big one, 1687, Newton achieves his supreme synthesis. He uses his brand new invention, calculus, to prove that the exact same math governing a falling apple also governs the orbits of the planets. It was a total game changer.
But here is where it gets really strange. Back in the 16th century, mathematicians invented complex numbers, numbers involving the square root of -1. At the time, they were viewed as just a formal algebraic trick. In fact, calling them imaginary numbers literally started out as a deprecating joke. But skip ahead to the 20th century, and boom, the absolute fundamental object of quantum mechanics, the wave function, is inherently complex valued. The Schrödinger equation absolutely requires them. This imaginary algebraic joke somehow became the indispensable language of physical reality. No way they saw that coming. And then there's the precision, 12. That is the exact number of decimal places to which quantum electrodynamics, or QED, accurately predicts the magnetic moment of the electron. The theoretical math and the experimental measurement match to 12 significant figures. To put that truly terrifying precision into perspective, that is the equivalent of measuring the distance from New York to Los Angeles and being perfectly accurate to within the width of a single human hair. It's just mind-blowing.
And this brilliantly illustrates the jaw-dropping predictive power of pure math. In 1961, physicist Murray Gell-Mann used an abstract 19th century algebraic framework known as group theory, which is basically a way to study symmetry, to classify known subatomic particles. When he mapped them all out, the math showed a specific hole in the pattern. The algebra strictly demanded that another particle literally had to exist to complete the structure. 3 years later, in 1964, the omega- baryon was actually discovered in a bubble chamber, perfectly fitting the exact properties that the pure math had demanded all along.
Section 2. The suspects. Interrogating the leading theories. So how do we actually explain this massive anomaly? Let's pivot to the major philosophical and physical frameworks that are trying to crack this case.
Now, before we can even try to explain why math describes nature, we really have to define what math actually is. Is it discovered or is it invented? Here are the main suspects. Mathematical Platonism, or realism, argues that math exists entirely independently of us, and we just discover it. Formalism completely flips it on its head, saying math is nothing more than human-invented symbol manipulation. Logicism tries to reduce all math to pure logic.
Intuitionism views it purely as a mental construction inside our own heads. And then structuralism suggests math is simply the study of abstract patterns, regardless of what the underlying objects actually are. So how do these ideas translate to the real world? Well, let's weigh two of the more deflationary theories here. First, the selection argument says, hey, there's no miracle, we just heavily bias our attention toward the math that actually works, and we throw away all the dead ends. On the other hand, the dialectic argument says math and physics have historically co-evolved, kind of borrowing ideas back and forth. And look, both of these are highly plausible, but here's the absolute crucial point. They completely fail to explain those stunning leaps we just talked about. Where pure math just sat unused in abstract journals for decades before suddenly perfectly predicting a brand new physical reality.
So let's look at two radically different approaches. Cosmologist Max Tegmark proposes what's called the mathematical universe hypothesis. He argues the physical universe doesn't just use math, it literally is a mathematical structure. For him, mathematical existence equals physical existence, the whole shebang. Contrast that with the anthropic view, which argues our human minds simply evolved to track physical reality in order to survive. So of course, the math our brains generate maps back to those physical patterns. But again, it's really hard to see how evolving to, say, count sheep helps us invent the infinite dimensional Hilbert spaces we absolutely need for quantum mechanics, right?
Section 3. The master key, symmetry. Now, if there is a deep, hidden bridge between abstract math and physical reality, this is undoubtedly the strongest clue in our entire detective story.
Let's define what we mean here. A symmetry is a transformation that leaves some essential feature invariant, or basically unchanged. Think about it. Rotate a perfect sphere, and it still looks exactly the same. At its core, mathematics is fundamentally the study of these invariants. And Albert Einstein shifted modern physics forever when he realized that rather than just looking for symmetries within physical laws, we should actually use symmetry to construct the laws of nature from scratch. It was a massive paradigm shift.
And let's see how this builds into something truly incredible. In 1915, Emmy Noether proved what might just be the most profound theorem in all of science. She mapped out the exact, breathtaking translations between mathematical invariance and physical conservation. If the laws of physics are symmetric over time, her math shows it directly dictates the conservation of energy. Spatial symmetry directly dictates the conservation of momentum. Rotational symmetry, that gives us angular momentum. It literally proves that the deepest features of abstract geometry are entirely identical to the deepest laws of physical reality.
And the result of Noether's brilliance leads us exactly here, the standard model of particle physics, which is our most complete description of fundamental particles and forces, is built entirely from abstract symmetry groups. Every single fundamental particle out there is essentially just a specific physical manifestation of these abstract mathematical Lie groups. An electron isn't just a tiny physical ball, it's a specific pattern of mathematical symmetry. The very atoms making up your body right this second are strictly governed by these abstract rules. Symmetry is without a doubt the ultimate shared logic between the human mind and the cosmos.
Section 4. The anomalies, where math breaks down. Now, what's really interesting about this slide is we have to maintain our intellectual honesty and interrogate the cold cases where mathematics completely and utterly struggles. It doesn't work everywhere.
Take a look at the massive contrast when we compare physics to biology. Physics deals with simple concepts like scale separation, universality, and reduction. The fundamental laws are incredibly elegant and they apply everywhere in the universe. But biology is completely messy. It's driven by emergence, staggering complexity, and historical contingency. The human genetic code isn't some elegant mathematical necessity. It's a specific, messy historical accident from 3.5 billion years ago. And this really proves that math's unreasonable effectiveness simply isn't guaranteed everywhere in nature.
And honestly, even within physics itself, we hit some really hard limits. For instance, the Navier-Stokes equations perfectly describe fluid flow, yet predicting turbulence remains an unsolved Millennium Prize problem. Then we have the profoundly difficult hard problem of consciousness. Right now, we have absolutely zero mathematical framework to explain how physical neural circuits give rise to the subjective feeling of pain, or the vivid experience of seeing the color red. And of course, there's quantum gravity. When you get down to the incredibly tiny Planck scale, the pristine math of general relativity and quantum mechanics completely clash and break down.
Section 5. The frontier, information, AI, and the future. As we look forward to the cutting-edge research emerging between 2024 and 2026, some fascinating new clues are popping up about the very fabric of reality itself.
The legendary physicist John Archibald Wheeler coined this great phrase, "it from bit." He was basically suggesting that physical reality fundamentally arises from information. Building on that idea, researchers like Stephen Wolfram are currently exploring if the universe might just be a giant computer running really simple cellular automata rules. We're also seeing these astonishing breakthroughs in something called holographic duality. This links the geometry of spacetime directly to quantum error-correcting codes. It strongly suggests that spacetime and physics might actually emerge entirely from underlying quantum information.
Which brings us to a deeply provocative final thought for this explainer. Right now, artificial intelligence systems, like DeepMind's AlphaProof, are actively discovering brand new mathematical theorems. Think about that for a second. If AI, a totally non-human entity, can discover pure math without us, does that definitively prove that mathematics exists entirely outside the human mind? Are we simply uncovering an eternal abstract architecture that the universe was built upon? We've really only scratched the surface here today, but I leave you to wonder, is the cosmic mystery of mathematics something we just invented, or is it something we discovered?